Okay. So the first derivative of a cubic function is quadratic, and the second is a linear function. Now, sometimes they can give you a question. In most cases, it will have a quadratic graph, and they can ask you from a quadratic graph to sketch the corresponding cubic function. So you need how to do, you also need to know how to move from a quadratic function to a cubic. Okay, in most cases, it's the relation between the cubic and the quadratic. But you can also involve the linear function. Okay. So I just want you to write this down. For example, okay, I have a function here that's x cubed plus 3x squared plus 2x. Okay, x cubed plus 3x squared plus 2x. Alright? So I'll just write here e.g. f of x equal to x cubed plus 3x squared plus 2x. Okay? Your first derivative will be 3x squared plus 6x plus 2. That's a quadratic. Okay? That's quadratic. The second derivative will be equal to 6x plus 6. And that's linear. Okay? Now, we are going to sketch all three. Okay? We're going to sketch all three, but I'm going to use a computer. Okay? Now, we are going to analyze the relationships. And then later, we can do a summary of the relationship. Okay? Make sure you pay attention. So, that's the cubic function. Okay, it has got a maximum turning point, then it has got a minimum turning point. So it's concave down, then concave up. Okay, this one here, it's concave down first, then it's concave up. All right. Now, okay, this software, it has got a slider. I need to change this. I think I need to change that equation. Let me put A there. Okay. Okay. Do you see that for the cubic function, if I put a equal to 1 here, you end up having a quadratic function. Okay. So let me change my slider now. Oh, in actual fact, I made a mistake there. Anyway, let me put x here. I'm supposed to have a x cubed like that. Okay. Right. So if your a is positive, like in this case it's equal to 1, you have the maximum turning point. Okay, which is x cubed plus 3x squared plus 2x. Then, if I move the slider, say to the left, okay, I can have something like that. I'm going to end up having a graph which is concave up and then concave down because the a value is now negative. So the shape change. The shape change from having a maximum turning point towards a minimum. Now we've got a minimum, then a maximum. Okay, so that's very important, knowing the effect of the value of a. Okay, I'm going to take it back to a equal to 1. Now, let me add now the first derivative. Like my first derivative, I'm going to call it g of x. Okay, so here you have your first derivative. I'm going to change the color there so that you can see it clearly. Okay, so you have your what? Your first derivative. It's quadratic, right? First derivative is quadratic. Now, let me ask the computer to just add these points. We want the turning points, right, of the graphs. Those are the turning points, okay, of the two graphs. So you have your minimum and maximum for the cubic graph. That's the value. Now, your point of inflection, okay. The good thing is that this software, it can help me to determine everything. So that's my inflection point. I just need to put my function there. So my function is f of x. Okay. So the computer is also determining the point of inflection, which is that point. Okay? Now, by observation, what do you notice in terms of the relation between the two? I'm talking about, let's say, the x values of the two graphs. What do you see? The x values of the two graphs. Let me remove this keyboard. Right? The x values of the two graphs. What do you see? Yes, Tesha?
The x value of the turning point of the quadratic is the same as the x value of the x-intercept, the point of inflection.
Yes.
X value.
So the x value at the point of inflection is equal to the x at the point of inflection of the cubic graph is the same as the x value at the turning point of the quadratic graph. So if you are given the quadratic graph and they ask you to sketch the cubic, you need to know that, okay, my x value at the turning point of this quadratic graph is the x value at the point of inflection. Can you write that down? Write that down. So that's your first point. Yeah, I'm not writing anything, just like relationship between quadratic or between the quadratic function or the first the derivative and the cubic graph. You can decide how you want to write it down. It's your book. Okay? But what you need to know is that the x value at the point of inflection of a cubic graph is the same as the x value at the turning point of the quadratic function. In that case, the quadratic function is your first derivative. So write that down. Right. The other point which I wanted to write for this graph, is not very clear though, is that the x values at the turning point of a cubic function, please write that down. The x values at the turning point of the cubic graph, the x values at the turning point of the cubic graph are the x-intercepts of the quadratic function. So the x values at the turning point of a cubic function, those x values that you see at the turning point of a cubic graph, they are actually the x-intercepts of the quadratic function. Okay? Here it's not very clear, but they're supposed to pass, this line is supposed to pass through that point, and that one is supposed to pass through that point. All right? So make sure you are aware of that. Another thing, I'm sure you can see that here the graph is concave down. Do you see that the quadratic function is a decreasing function? So when the graph is concave down, always, okay, always, the first derivative must start as a decreasing function. The y values of the first derivative are decreasing, okay, when the graph is concave down. So the first derivative, which is quadratic, is a decreasing function when the graph is concave down. Okay. Now on the other side of the turning point of the quadratic graph, the quadratic graph is an increasing function. Okay, it's an increasing function, and the cubic graph is concave up. Okay, now let's change now the value of a from being positive, okay, even if I take it there, you're going to have the same scenario, okay, that I just explained. So you can see now when a is 2, it's not coming out very clear because the screen is not a little bit small. Now the graph is a decrease, the quadratic function is a decreasing function. I'm talking about when a is 2, right? It's 2 concave down. Okay? So when the first derivative is a decreasing function, the cubic graph is concave down. And then when the first derivative is an increasing function, the cubic graph is concave up. Okay, let's make it negative. If I make it negative, like that, okay, I'm talking about the value of a, right? Now, the shape has changed. Okay, let me bring it down so that it can come out clearly. And then let me take that there. Right, now your cubic graph is now concave up, then concave down. Now, the quadratic, when a was positive, we had a minimum turning point for the quadratic. Okay, with the minimum turning point. But now a is negative, we now have the maximum turning point for the quadratic. Okay, so the quadratic is an increasing function. Okay, is an increasing function when the cubic graph is concave up, which is also true when a was positive. So when the first derivative is an increasing function, the cubic graph must be concave what? Up. And when the first derivative is a decreasing function, the cubic graph must be concave down. Always. That's very important, because if you are given a question with the quadratic graph with no cubic graph, if you are asked to sketch, you need to know how the cubic graph is going to look like from the quadratic. And it can be a bit confusing. So make sure you take note of this and you write it down. Because sometimes you might not have it in textbooks. What I'm telling you now is probably not in textbooks. You might not find it in some textbooks. Okay? So, when the quadratic or the first derivative of a cubic function is an increasing function, the cubic graph will be concave up. When the first derivative is a decreasing function, the cubic graph will be concave down. Okay? All right, let's move on to, let's add the second derivative now. The second derivative. So my second derivative, I'm going to call it h of x. Okay. H of x. In fact, let me call it h of x. H of x, that will be derivative. Now, in this case, it's going to be I'll put the derivative of the quadratic. to make it linear. So it will be g of x. Okay, so you have that. The one in red. Let me make it bolder. Right, I want you to be aware that for this graph here, when a is -1, the point of inflection has changed. Okay, it's now at x equal to 1 and y equal to 4, which is this point here. Right? I hope you can see that. Okay, now, what do you notice in terms of the three graphs? Do you see something which is common here? Yes, then.
The x-intercept of the second derivative is equal to the x value of the point of inflection and the x value of the turning point of the quadratic.
Right, now here, the x-intercept of the second derivative, this is very important. The x-intercept of the second derivative, okay, is the same as the x value at the turning point. It's also the same as the x value at the point of inflection of the cubic. So the x value the x-intercept of the first derivative is the same as the x value at the turning point of the quadratic. It's also the same as the x value at the point of inflection. Okay, so sometimes if they give you a linear function and they ask you, well, what's the value of x at the point of inflection, you can determine it. Okay, if the graph is there. Okay, please write that down. The x value, or rather the x-intercept of the second derivative is the same as the x value at the point of inflection and at the turning point of the quadratic function. You can use it your own words. The x value here, this is the linear. The x value there, that's the quadratic. So this is the cubic, that's the point of inflection, and that's the turning point of the first derivative. Now, I want you to check this now. Remember, if you were listening carefully, or if you went home, you listened to the video, one of the videos, I think it was the one on point of inflection. And I want you to pay attention carefully so that you know where the inequalities come from. Now, do you see that the linear function, okay, in the fourth quadrant, it's what? Positive. The y values. I'm talking about the y values. The y values of the linear function in the fourth quadrant, they are what? They are positive. Okay? And in the fourth quadrant, the cubic graph, okay, I'm going to remove the in the fourth quadrant, listen carefully. In the fourth quadrant, y is negative. So for the second derivative, the y values are negative.
So the y values are negative, right? They're not positive. Because you said positive first and then now you changed it to negative.
Maybe it was a mistake if I said that. So I'm going to correct it now. I'm going to correct it now. In the fourth quadrant, y values are negative. Okay? The y values are negative. Which y values am I talking about? The y values of the second derivative, which is a linear function. They are negative. Okay? Now, do you see that our cubic graph is counted down? So when the y values of the second derivative are negative, the cubic graph is counted down. That's why I can write f double prime of x is less than 0. That f double prime of x, it represents what? Y. So what this means is, the y values of the second derivative, when it's concave down, they will be negative. I hope you are following. So this is where the inequality originates from sketching. Now, and then in the first quadrant and in the first and in the second quadrant, the y values are going to become what? Positive. In the graph, as you can see, you see from just after this point to the left, it will become concave what? Concave up. That's why we can write, for that interval, we can write f double prime of x is greater than 0. So when the y values of the linear function are positive, the cubic graph will be concave up. Okay? Now let's change. Remember, we are talking about a case here when a is negative. Let's make a positive and see what happens. The linear function is going to change, the shape will change. See that? So what happened? We had a negative gradient when the a value of the cubic graph was negative. Okay? Now the a value is positive. We now have a positive gradient for the linear function. And our cubic graph is going to be concave down, then concave up. Okay? Now, if you look at the y values, okay, in the third quadrant, they are negative, and the cubic graph is concave down. So, if double prime of x is less than 0, when the graph is concave down, okay? Then, as the y values become positive, I'm talking about the y values for the linear now. As they become positive, the cubic graph becomes what? Concave up. That's why we write f double prime of x is greater than 0. Okay? Right, so I'll see you. Then I'm going to give you homework, but I'll send it on the WhatsApp group. Okay, on sketching.